Hello again. This is Nicky Williams, who will from CEA List University, who will be presenting the last paper of this test generation session. Okay, titled towards exhaustive branch coverage with PathCrawler. Okay, this is a short paper. Okay, and there will be some questions that Nicky will answer to you. Okay, afterwards. So, the stage is yours.
Sorry, I'll find the right.
Okay.
Yes, there we are. Okay, hello. I'm going to talk about exhaustive branch coverage with PathCrawler. So I'm going to start by saying why exhaustive branch coverage is an interesting problem. There are lots of test generation tools now that achieve high coverage scores, but here we're talking about covering all reachable branches, and for branches that are not covered, providing an explanation. And this is either a demonstration by a prover or a solver that the branch is unreasonable, or in the worst case, if the prover fails or the solver times out, it's the formula that would have enabled us to cover the branch. And this is often needed, in fact, for certification of safety critical software. If we need to be sure that we found all dead code, all assertion violations. In fact, there are many verification problems where we have numerous test objectives and we have to either provide a witness of reachability in the form of a test case or else demonstrate that they're not reachable. So I'm going to remind you, first of all, about how we generate test cases using symbolic execution, constraint solving, and the Concolic method. And I'm going to demonstrate that on this little example of a C function, which you can see with the associated control flow graph. And in this slide, you can see that I've changed the notation on the control flow graph. So true branches are plus, false branches are labeled minus, and the conditions are just labeled with the line number. So if we wanted to find a test case that would cover the path +2, +4, +6, we would use symbolic execution to convert the conditions and the assignments in that path into constraints over the input values. The input value here, there's just one, x, and we call it x0 because it's the value at entry to the function of x. And we send that conjunction of constraints to the solver, and any solution that the solver finds will be a concrete value for x that is a test case that will activate this path. However, if we send the solver the constraints which correspond to the branches +2, -4, it will say that this is an unsatisfiable conjunction of constraints, and that is a demonstration that all paths with the prefix +2, -4 are infeasible. Now, another way to look at this is to, instead of the control flow graph, look at the tree of execution paths, which I show here for the same example. And obviously, in this tree, every branch in the control flow graph, except the first one, has several occurrences in this tree because it has several possible prefixes. And in order for a branch to be unreachable, all the prefixes in this tree to that particular branch must be infeasible. Now, if we were to use Concolic generation for test case generation, then we'd start with asking the solver for just some arbitrary input value. And let's say it says x -2. We then run that test case and we see that it covers the path +2, +4, +6. And what we do is we look at the nodes in this path and we decide in each case whether to take the branch from the test case or whether to do what we call flipping, i.e. try to find a test case which takes the opposite branch, a new case. So we can flip nodes in any order, but let's say we do this depth first. What that means is that we start off by using the constraints for the branches that were taken, +2, +4, and then the last constraint, instead of +6, we flip and we use the constraint for -6. And we send the constraints over those constraints, and it says that this is in fact an infeasible conjunction, unsatisfiable. So we go back up to the previous node and we try to find a solution to the constraints corresponding to +2, -4, but that's also unsatisfiable. So we go back up and we ask the solver for any solution to the constraint for -2. And we don't say which branches we should follow in the rest of the path. Just any path that starts with -2. So the solver returns a solution, let's say it's x equals 1. And in that case, the rest of the path, the suffix that is followed by that path is -4 plus 6. And we then start exploring that new suffix in exactly the same way, and so on. So concolic generation is efficient because we detect the shortest infeasible prefixes, and that enables us to prune this tree. And because in the tree, we call the solver just once, and solvers are NP complete. And also, if we have incremental constraint solving, we can store on a stack the constraints that allow us to reach each node in the tree. And then when we want to flip the node, we can go back and recover the constraints from the stack so that we don't have to rebuild the constraint problem every time. But concolic generation was designed for path coverage, and with branch coverage, we have a problem, which is that unlike in path coverage, we don't need to actually flip all the nodes. And we don't know which suffix will be covered when we do flip a node. So when we get to a node, and if the opposite branch is not covered yet, then we know that if the flip is successful, we're sure to increase coverage by at least that branch. But if the opposite branch has already been covered in a previous test case with a different prefix, and if the flip is successful, we don't know which other branches will be covered in the suffix, and we don't know whether any uncovered branches will be covered. If we do a lot of hopeful flipping, we run the risk of what we call path explosion, that is, generating blindly more and more cases which cover more and more paths without actually increasing branch coverage. So for branch coverage using concolic generation, the question is, which branches do we flip and when, in order to limit these potentially expensive solver calls and, as a consequence, the number of tests that are generated and which have to be treated. So we had the intuition that we could limit solver calls by limiting hopeful flipping. And so we implemented successive strategies to do that in the PathCrawler concolic tool, which uses constraint logic programming. And the first baseline strategy was the one I just showed you. And the first new strategy we tried is what we call eager flipping, because it does the opposite. It goes down the newly generated path suffix, and it tries, first of all, to flip each branch. And if the flip is successful, it will go and treat the newly generated suffix and so on, before coming back to the original suffix to go down to the next branch and trying to flip that. And then we tried a strategy which was a little more intelligent, because if it was a case of hopeful flipping, we would first of all check whether there were actually any uncovered branches in the subtree rooted in the flipped prefix. And if not, don't bother. And then with the else strategy, we tried to delay hopeful flipping as long as possible. So we would go down the path suffix doing any eager flips that we could do. And only when we backtracked back up the suffix would we do hopeful flips. And finally, because the problem with all those strategies was that we would treat the newly generated suffixes before going back to earlier suffixes, and maybe in those earlier suffixes, it would have been easy to cover certain uncovered branches, we tried to have a fairer strategy by implementing the else strategy in a multi-threaded way with one thread for each new suffix. And we only activate threads which are doing hopeful flips when there are no more threads doing eager flips, so that we leave them as late as possible. We tried these different strategies out on a few examples of C functions, and in two particular cases, the ones we call A and T, it's the same function with and without unreachable branches. Excuse me. So if we take the depth first as the baseline, that's 100% on this chart, we can see the relative number of hopeful flips and solver calls for each strategy and each example. And the first thing we see is that there is indeed a correlation between hopeful flips and solver calls. So that is borne out by these examples. And as for multi-threaded else, it is the best strategy for hopeful flips and solver calls on all the examples except the A examples. And that's because, as you can see, in fact, the effect of the different strategies does vary a lot according to the cases. And that is because of chance coverage, which we can't do much about. So in more recent work, we've been extending this multi-threaded else strategy with new mechanisms to prune the search tree even further. Okay, thank you very much.
Thank you very much for your presentation, Nikki. Well, others might have time to write the questions in the chat. Okay, I would like to ask. You talk it, or you say that the solver calls were reduced. Okay, but I do not have an idea of how much really running tests are reduced. Okay, so do you have an idea on this, or are we talking here about second, minutes, hours? Because in my experience, okay, some solvers might take long running times, okay, to accomplish their or give you a result. Okay.
Well, I would really say the opposite, actually. In a lot of the examples that I run, the constraints are often quite trivial. But the problem is that every now and then, you get a constraint which isn't trivial, and it's very difficult to predict which branch condition that will be. And then, of course, the solver gets stuck. The number of cases was very closely correlated as well to the number of solver calls and hopeful flips. It was much the same. And these are quite small examples, so they all ran in a couple of minutes. But I used these small examples because it enabled me to track lots of different things that were going on and see what the effects really were of these different strategies.
Okay, thank you. I don't know if there are anyone who wants to ask something in the chat.
Anyway, if you have some interesting examples that make the solvers really get stuck, I mean, I take them happily, because I have a couple of floating point examples which the solver doesn't like very much. But it's difficult to find them.
So Tony is asking if the tool is available, and if so, for which languages?
Is it available? There's an online version of PathCrawler which is available as a sort of server. So you upload your code and it generates the tests. But it's a very old version now. So one day I'll update the online version when I get the time. Otherwise, it only treats C at the moment. Otherwise, you can send me an email, and if it's for research purposes, I can send you an evaluation version of the tool, today's version of the tool.
Okay, thank you, Nikki. I don't know if we might have time for just one more question, because in 1 minute the room will close. And remember that Nikki will be transferred to a discussion room where the attendants, can join. Okay, you will see a pop-up, in the chat to join that room, in case you want to ask some other questions. Okay. So thank you very much for your presentation. Okay.
Bon appétit.
It's lunchtime here in Spain as well. So I will talk to you. Well, those of you who will attend this afternoon, the mutation testing and debugging session, I will be chairing that session as well. So see you this afternoon.